So good morning class. So today our topic is Compton scattering, which is one of the breaking moment in the modern physics. Okay. So after this short lecture, you will be able to learn the experimental setup for this Compton scattering experiment and the result of the experiment, what the experiment gives us. Okay. Okay, so let's start with the experimental setup. Okay, we will see a short video and see what's happening in the Compton scattering.
Scattering in picture. Okay, a photon of incident wavelength lambda I falls on a target electron at rest. The electron recoils at certain angle phi with respect to the initial scattering line, and the photon scatters off the electron with an angle theta with a different wavelength lambda f.
So let's first learn about the experimental setup. Okay, so we have an X-ray source here which emits high energy photons. Okay, with energy E1, EI incident and with wavelength lambda I. The photons, remember, this is not a one photon. Okay, there is a stream of photons coming in from the X-ray source. It's a target. Target is usually a carbon or a molybdenum or a tungsten target which contains many atoms and hence many electrons. Okay, so the high energy photons hits a target electron. The electron gets scattered, recoils in certain direction, and the photons, which was this, get scattered off the electron in certain directions. Okay, so the photons, streams of photons are coming in, hitting the various electrons of the target, and the photons get scattered all throughout the lab. Okay, now what we do as an experimentalist, we catch these scattered photons. Okay, now obviously, if EI is the energy of the incident photon, the photon is transferring some of its energy to the electron, right? So the ES, its energy is getting diminished, right? So ES is of course less than EI in the process, right? So we place the detector in such a way that we catch the photons along various angles. Okay, say for example, we keep the detector at an angle theta, which is a variable. Okay, and see how many photons are coming in that particular direction. Okay, so we calculate number of photons, 1, and 2, the wavelength of the scattered photon. Right, so we keep changing the position of the detector. Say I keep at theta equals to 0 degree along this line, and see how many scattered photons are coming along that direction. We keep the detector at 90 degree angle, theta equals to 90 degree, and see how many photons are coming in along these directions. Okay, so we calculate the number of photons along a particular direction, along certain theta, and see the wavelength of the scattered photon, measure the wavelength of that scattered photon. Okay, so that's the experimental setup, that's the goal of the experiment. Right, is there any question? So next, we move on, what was the result of the experiment. Okay, so let's see the result of the Compton experiment. Okay, so remember, what did we have? We have this scattering line, electrons flying off certain direction and the photons getting scattered along certain directions. We have detectors here, right? Now we plot for 3 different positions. Okay, so these 3, nothing special with these 3, but we plot for when the detector is at theta equals to 0 along the scattering line, when theta equals to 45 degree, and when the detector is here, say theta equals to 90 degree. So for these 3 distinct positions, we plot the wavelength of the photon versus the intensity. Intensity means number of photons along a particular line, of action, direction. Okay, so that's what we are catching, right? So we see when theta is 0 along the line of scattering, there is only one peak. in the wavelength. Right? Now, as we go on increasing, when theta equals to 45 degree, say for example, we see that there is too little peak, okay, which is a shift from one another. So that is called delta lambda in wavelength. Okay, so this shift is called Compton's shift. As we go on increasing the scattering angle, when theta becomes 90 degree, we see the peak becomes much more shifted. Okay, this is a wider shift. So this one small peak is the incident photon wavelength, and the other one, larger one, is the scattered photon wavelength. So as we go, when the scattering angle is more, the shift of the photon's frequency or the wavelength is much more larger. When the scattering angle is small, there is no shift at all. So this is minimum shift or no shift, no Compton shift, and this is maximum Compton shift. Shift in wavelength. Right. So that is the result of the Compton scattering experiment. Is that clear? Let's summarize what we have learned. In Compton scattering, high energy photons get scattered off stationary electrons. Remember, the electrons are assumed to be stationary. We catch the photons traveling in various angles. Okay, we catch them with our detector and count the number of photons coming in along that particular line, and also measure their wavelength. Okay, the scattered photon wavelength, the incident photon wavelength is already known. Then we plot the intensity. Intensity means number of photons along a particular direction. Intensity versus wavelength graph for various scattering angles. Theta equals to 0, theta equals to 45 degree, theta equals to 90 degree, so on and so forth. We see that with the increase in scattering angle, shift in the wavelength increases. Okay, so when theta equals to 0, there was no shift at all. When theta equals to 90 degree, there's the maximum shift. Right? So that's what we learned from the Compton scattering experiment. In the next class, we will do the analytical, theoretical calculations and try to arrive at the result. Okay? Okay.